Example: apply the simplex method to solve the following linear programming problem. Maximize z equals to 13x1 plus 23x2 plus 29x3 subject to 6x1 plus 5x2 plus 3x3 is less than equal to 26. 4x1 plus 2x2 plus 5x3 is less than equal to 7, and x1, x2 and x3 greater than equal to 0. Equation 1. Also write the solution of the dual of the above problem from the final table. Now taking slack variable x4 and x5 and then reduced following equation equals to 6x1 plus 5x2 plus 3x3 plus x4 equals to 26, and 4x1 plus 2x2 plus 5x3 plus x5 equals to 7. So simplex table is CJ 30, 23, 29 and 0, YB, CB, XB, Y1, Y2, Y4, beta 1, Y5, beta 2, Y4, C4, 26, 5, 3, 1 and 0, and C, Y5, C5, 0, 7, 4, 2, 5, 0, 1, and Z equals to CB, XB, CB into XB equals to 0, XJ equals to 26 and 7, and delta J equals to 30, 23, 29, 0 and 0. Here, since 30 is the most positive element entry, so this is key column, and minimum ratio 26.6 and 7/4 is the minimum for 7/4, so this is the key element. So y1 will enter and y5 will come out. So in place of 4 we will make unity, and in place of other entry we will make 0. So the entries of the corresponding to that after suitable multiplication and division: 7/4, 1, 1/2, 5/4 and 1/4, and 31/2, 0, 2, 9 minus 9/2, minus 3/2. C Z equals to CB into XB, 210/4 equals to 105/2. Delta J 08 minus 17/2, 0 and minus 15/2. Since 8 is most positive entry, so this is key column, and so the 7/4/1/2 and 31/2/2. So the minimum ratio is this, so 1/2. So the y2 will enter and y1 will come out. So now we will proceed the next part of the video from here. So here we have delta 1 equals to c1 minus z1 equals to 30 minus 0 into 0 plus 30 into 1 upon 0 equals to 0. So delta 2 equals to c2 minus z2 equals to 23 minus 0 into 2 plus 30 into 1/2 equals to 8. Similarly, we can find delta 3 equals to minus 17/2 and delta 4 equals to 0, and delta 5 equals to minus 15/2. Since delta 2 is greater than 0, so the positive improvement is possible, and the vector y2 will enter the basis of the yb. In order to find the vector of the basis yb, we should let us write to compute xbr upon yrk. The minimum of j is xbi upon yjk, and yjk is greater than 0 where j equals to 1 and 2 and k equals to 2, or xbr upon yr2 equals to xb2 upon y22, which implies r equals to 2. Therefore the vector b2, that is y1, will leave the basis of the yb. The leading element of is 1/2, which has been shown in the second simplex table and the given above. Now we have to find the third simplex table as follows. In place of 1/2 make unity, and in place of 2 we will make 0 after suitable multiplication and division. So we have here 1 and here 0. The rest of the entries are 7/2, 2 and 5/2, 0, 0, 0 and 1/2, 17/2, -4, 0, -19/2, 1 and -5/2, y4 and c4 equals to 0, y2, c2 equals to 23, z equals to cb, xb equals to 23 into 7/2 equals to 161/2, xj equals to 7/2 and minus 7/2 and 17/2, delta j equals to -16 and 0 and -57/2 and 0 and -23/2. Here delta 1 equals to z1 minus c1 equals to 30 minus 0 into -4 plus 23 into 2 equals to -16. Delta 2 equals to z2 minus c2 equals to 23 minus 0 into 0 plus 23 into 1 equals to 0. Similarly, delta 3 equals to -57/2 and delta 4 equals to 0 and delta 5 equals to -23/2. Since none of the delta j is greater than 0, so the optimal solution has been reached, and the optimal solution of the given primal problem is maximum on z equals to 161/2 and x1 equals to 0 and x2 equals to 7.2, x3 is 0. To read the solution of the dual of the given primal problem from the final, that is from the third simplex table given above, from the delta j's with the sign changed for the slack variable x4 and x5 in the final table above, the solution of the given dual of the given problem are w1 equals to minus delta 4 is 0 and w2 equals to minus delta 5 equals to 23/2 and z equals to zd equals to maximum of z equals to 161/2.